again, if the limit as n goes to infinity of a sub n does not exist. Now think about that. It can either not exist, and I'll show you what I mean by that. Excuse me. Does not exist. This is either not exist or equals plus or minus infinity, which again don't exist. So this is being a little bit redundant, but we got to be real careful here. I'll show you what I mean here in just a sec. Then we say that the sequence a sub n diverges. Okay? Now, let me give you an example. These are actually pretty easy to deal with if you think about it, but they can look really, really nasty. Let's see. I want something good. How about let's take the cosine of let's do this one. I like this one because this one's going to make us think a little bit. Let's let a sub n. Got to come up with a fun one for you guys. Let's do the cosine of 1 over n. And let's put a negative 1 to the n in front. All right? So the question is, does it converge or does it diverge? Well, it's easy. All I do is I take the limit as n goes to infinity of this guy, negative 1 to the n, cosine of 1 over n. Okay? As n gets huge, hopefully you see that this guy right here, this turns into the cosine of 0, right? Now remember, I'm letting n get big, but n is still just positive integers, right? We start at 1, we go to 2, da-da-da-da-da-da-da, right? So what's happening? My sign is switching. So as n goes to infinity, this turns into the cosine of 0, which is positive 1. But as I plug numbers in, what I end up with is way out at infinity. I end up with a bunch of terms, then comma, dot, 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 and then I get some numbers that are really close to 1, negative 1, 1, negative 1. Guess what? Et cetera, forever. I guess I should go comma, dot, dot, dot. Comma, where am I? Comma, dot, dot, dot. Which means I don't go to a number. But Ripley, I go to 1. No, I don't, because the next term's negative 1. But Ripley, I go to negative 1. No, I don't, because the next one goes to 1. You see how that works? So this limit right here, this guy, this limit, does not exist. Therefore, which implies that a sub n is divergent. So it's real simple. Take a limit. If I'm trying to determine, the moral of the story is, let's get out of this obnoxious red, get some black in there. If I want to know if a sub n converges or diverges, just take the limit as n goes to infinity of a sub n. Now, watch this. I'm going to put a nice little button on this whole thing. Put a button. Put a ribbon on this whole thing. Remember here how back here we looked at these. We said, hey, these things smell a whole lot like functions, don't they? They smell like functions where all we're putting in are integer. So this would be like a real valued function of an integer variable. In other words, we're using an independent variable, which is an integer, and we're plugging it into a function. Well, think about that. If I can marry a function to a sequence, then everything that's true of the function is true of the sequence, at least the function for the integer values. So think about what that says. What we have is a theorem. All right, here's our theorem. Our theorem says this: if the limit as x approaches infinity, always positive infinity, right? Because we start at 1, we go to 2, we go to 3, all the way out to infinity, of f of x equals L. In other words, it exists. I'm going to write that in. I'm going to keep writing that in. Whoops. Exists. And a sub n equals f of n, right? Where, and ooh, we're going to get fancy math speaky here, where n is an element of the positive integers, right? Then the limit as n goes to infinity of a sub n equals L as well. they both get there. Let's go back to our 1 over n. Remember, a sub n equals 1 over n. Remember when I grabbed that guy? Well, what are we really doing? Well, this is f of x equals 1 over x, and all I'm doing is I've got x equals 1, I got x equals 2, I got x equals 3, and what am I doing? I'm popping up here, grabbing the point 1 comma 1, popping up here, grabbing the point 1 comma 1 half, up here, whoops, grabbing the point, what did I say, 1 comma 1 half? Yell at me, you guys, that's 2 comma 1 half. Grabbing the point 3 comma 1 third, right? So think about these points, these points that are produced by our sequence, as just being these little dots, almost like little jewels on this string that is our function. Wherever the function goes, these dots go as well, right? And that's why this theorem works. It makes total sense. That's the coolest part. So in other words, what's the moral of the story? All right, let's do a little sub-theorem. Think of it this way. What does this imply? If a sub n equals f of n, and f of x converges at x equals infinity, as x goes, let's do it that way, as x goes to infinity. Yeah, that's bad math speak right there. Now I'm just taking some liberties. You got to yell at me with that garbage. As x goes to infinity, this implies that a sub n converges as well. It's a wonderful tool. If you just think about sequences as just being these sets, right? The a sub 1, a sub 2, a sub 3, you're missing half the picture. And you're missing darn near all of the tools. Because the main tool is for us to be able to marry sequences to functions. Being able to marry sequences. We've been doing functions since algebra 1, since pre-algebra. Let's use them. Let's not just discard them. But let's make sure that we use them fully. So, now think about this. As another super powerful bit of juju that we can use is if I marry a sequence to a function, then all of the limit laws for functions apply to sequences. If I take the limit as n goes to infinity of a sub n plus b sub n, well, remember, the limit of the sum is the sum of the limits. I'm not even going to screw around because there's no such thing as subtraction. It's just addition with negative terms, right? So the limit of the sum, limit of the sum is the sum of the limits. So all those nifty little tools that we discovered about limits back in differential calculus, we now get to apply, which is awesome. Again, limit as n goes to infinity of c times a sub n is equal to c times the limit as n goes to infinity of a sub n. So cool, right? Limit, you know, product, right? And we got quotients in there too. Hopefully you remember that, of a sub n times b sub n is equal to the limit as n goes to infinity of a sub n times the limit as n goes to infinity of b sub n. What a powerful, good tool, huh? I'm not going to bore you with too much else, but we'll get there. N goes to infinity of a sub n divided by b sub n is equal to the limit as n goes to infinity of a sub n divided by the limit as n goes to infinity of b sub n, so long as the limit, so if the limit as n goes to infinity of b sub n does not equal 0. And then we got all remember the continuous function thing that we like so much, that we used in L'Hopital's a whole bunch, of a sub n raised to the p. This is equal to what do we got? This is the limit as n goes to infinity of a sub n, all raised to the p. All right? That's lots of fun. Hope you enjoyed that. Okay, now let me give you one more theorem and then just kind of show you how well these work. And then basically we've got some just interesting little definitions to do, and then we're all set. Okay? Okay, this is a really powerful theorem too. It is the theorem if the limit as n approaches infinity of the absolute value of a sub n is equal to 0. Now it's got to be equal to 0. If it's not equal to 0, we are screwed, as it were, because then it's a lie. Okay, and I'll show you what I mean. Well, I actually showed you an example earlier. It's got to equal 0 or we're dead. If the limit as n goes to infinity of absolute a sub n equals 0, then this implies that the limit as n goes to infinity of a sub n also equals 0. Okay, now why is that only true? Think about this. If I have, let's see, a function, remember I can marry sequences and functions. If I've got a function that's going, now watch this, I'm going to cheat a little bit here. Watch this. All right, so here's my function, but it jumps around with as my integers change. So I got a value here, and I got a value here, and I got a value here, and I got a value there. See how that works? So this is my, let's just say that this is my f of n. If I take the absolute value of that, what happens? Well, these positive terms would flip up here. Get out of there. These positive terms, or excuse me, these negative terms would flip up here and become positive. And what we end up with is this nice value heading towards 0. Okay? That's kind of that's a cool little graphical example of why that happens. In other words, if the absolute value, if the positive side heads for 0, even if this thing jumps around back and forth, then it has to head for 0 as well. It's got no choice. However, watch what happens here. What if I've got some L here, let's call this L1, and I've got some L2 here. And let's say that I've got, well, I'm going to start with this. Let's say that I take the absolute value of f sub n. This guy right here, by the way, was supposed to be representative of f of n. I say f sub n. Sorry, man, my words are escaping me today. All right, so if I take the limit as n goes to infinity of the absolute value of f of n, and let's say that it heads for L1, right? The problem is what we did is we took all of these negative values down here, right, that may have done something like this, and when we flipped them up, they headed for L1, right? Now think about this. Out at infinity, what's going to happen? I'm going to have points that were produced from the positive half of f of n, excuse me, and then these points that were produced from the negative half of f of n. So way out at infinity, what we're doing is we're jumping back and forth between L1, L2, L1, L2, L1, L2, L1, L2, even though the limit as n went to infinity of absolute f of n equaled L1. Notice that L1 is not equal to 0. That's a really good analogy for bringing it back to this too. You can't make that same argument because way out here at infinity, what is my function doing? It's going closer to 0, 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 on both sides of 0. In this case, that doesn't happen because it's bouncing back and forth between L1 and L2 as n gets really, really big. All right. However, this theorem is hugely, hugely useful. I mean, for example, let's say let's go -1 to the n times 2n plus 1 over, let's go 2n squared plus 1 over 4 minus n squared. Converge. Great problem. Wink, wink. Might see a problem like that again. Well, does it converge? Okay. Well, if we look at this, look close. I'm going to use this property. All right. Ooh, wait. I'm sorry, you guys. I want that to be n cubed. N cubed. Well, this -1, especially when you first start playing with it, can get really confusing. So let's look at the absolute value of -1 to the n 2n squared plus 1 over 4 minus n cubed. And what happens? Well, that's just 2n squared plus 1 over 4 minus n cubed. You agree with that? Just gets rid of this negative thing, right? Now that implies, follow me up this way, would you?